This loop unrolling, is this done by the compiler or by the assembler?
It is, I don't know. Yeah, so compiler converts it to assembly. Assembler converts it, it can happen at any levels, but I would say compiler is better. Because assembler is just gonna do the machine code translation, right? It just goes from assembler to binary. You know the answer?
Yeah, so the compiler typically has multiple optimization steps or optimization modes. If you like, especially with G++ and GCC, if you specify like -O, it has these optimizers that will help with unrolling, loop unrolling, all kinds of different things like setting variables to static, like values before you even like get to the assembler. Like it assembles it into like static values in the actual assembly code rather than having like dynamic variables or something.
That makes sense, yeah. I forgot about the optimization that you can do at the dash. One of the optimizations is actually loop unrolling, so that means it happens at the compiler level. Okay, so effective CPI. Now we talked about the CPI. We said that we had the clock per instruction, we had an example that already gave us the effective CPI, but how do we calculate the effective CPI, right? So different workloads have different instructions. Different instructions need different number of clock cycles. We already covered that part. Effective CPI is this simple calculation which gets the CPI of a specific instruction class. Let's say load a store. We say load a store needs 10 clock cycles. And then we find how many load and stores we have in that workload. So we have how much of that workload, that specific instruction class, how much it contributes to the entire workload, right? Is it 20% of the workload? Is it 50% of the workload? So if we have that proportion, and if we have the CPI for that instruction class, then we can calculate the effective CPI. How? Maybe we can understand it better with an example here. So we have an encryption workload, and we have an ARM processor that wants to take care of this encryption task. We have three types of instruction class instructions. We have integer instructions, floating point instructions, and data transfer instructions. The CPI for integer instruction is 4, the CPI for floating point instructions is 8, and the CPI for the data transfer instruction is equal to 10. We have 50% of the workload belongs to integer instructions, then we have 30% for floating point and 20% for data transfer. But this completely depends on your workload. If you have a machine learning workload, things can change in terms of the data transfer, integer, and floating point, right? But let's say this encryption task has this kind of workload. So let's calculate the effective CPI. I think it was muted. So let's calculate, Mama Reza, if they sent an email, can you reply back and see if they can hear it now? Yes, sorry. So let's calculate the effective CPI. Based on this equation, we have the CPI for integer is 4, the proportion is 50%, which means 0.5, that's the ratio. So we multiply 4 by 0.5, then we multiply 8 by 0.3, 30%, and multiply 10 by 0.2 and add all of them, right? So 4 times 0.5 is going to be equal to 2, then we have 8 times 0.3, 2.4, and 10 times 0.2 is going to be 2, and then if we add them, we're going to get 6.4. So this effective CPI for this workload is 6.4. What is the IPC? How can we calculate IPC? 1 divided by this, by CPI. But this is the IPC. And it means on average, every instruction in this workload needs 6.4 clocks. Right? We really don't have 6.4 4 clocks. As you can see, it's always an integer value. When we get the effective CPI, this can be a real value. Any questions? All right. So now let's practice. We have a program that has 40% arithmetic instructions. Each of them need 5 clock cycles. 30% branch instructions. It takes 2 clock cycles for each of these guys. We have 30% data transfer instructions that needs 12 clock cycles. And the program has 20,000 instructions, and it is running on a CPU with 3 gigahertz clock. What is the execution time of this program? Okay, so let's solve it together. We have this equation right here. We already have the number of instructions from here. Then we have the clock. We don't have the clock cycle time, we have the clock frequency. What it means is that to find the clock cycle time, we have to do what? We have the frequency, we want to find the clock cycle time. What should we do? Divided by that, yeah. So if I have 20,000 here, I'm good. Don't know this yet, and this is 1 divided by 3 gigahertz, which is 10 to the negative, 10 to the 9, right? So now what we need to do is finding the effective CPI. To find the effective CPI, we have to see what classes of instructions do I have. I have arithmetic instructions. That need 5 clock cycles. And they have the workload as 40%, which is 0.4. Then I have the branch instructions. It needs 2 clock cycles and the workload is 0.3 of the entire workload. And then we have data transfer. It needs 12 clock cycles, and it is, again, 30%. So what you need to do, you need to multiply these guys, and then add them to get the effective CPI. If you do this, you're going to get 6.2. Yeah, so you're going to get an effective CPI of 6.2. And now you have everything to calculate the execution time. You can do the math later yourself. 20,000 times CPI divided by 3 multiplied by 10 to the 9. Any questions? All right, so let's have an example that shows that if you have a higher frequency for a computer system, it doesn't necessarily mean that the computer system is faster. What we need to do when we have these metrics, we shouldn't get too excited when we see like better frequency or whatever. We have to somehow convert everything to execution time before making a decision. You get all these metrics. The only thing that you can be sure of, if you have the execution time, you can find the relative performance. If you don't have it, don't get too excited. Just make sure that you have to somehow find the execution time and then find the relative performance. Okay, so this is an example. We have a signal, a Wi-Fi signal convolution task that needs 1,000 of instructions on Intel and AMD devices. Intel has a clock frequency of 1 gigahertz and an effective CPI of 4, and AMD spend more time, because this is just random example, it's not a fact. So AMD spend more time to increase the clock frequency, and the clock frequency is 2 gigahertz now, but the CPI is 10, so instructions are not very efficient, but the clock frequency is better. So which processor provides higher performance for that Wi-Fi convolution task? They have obviously the same instructions, so we have to relate everything to execution time. If we calculate the execution time for Intel, it is 1,000 instructions multiplied by CPI multiplied by clock frequency, by clock cycle time, which is 1 divided by clock frequency, and you get that many seconds. For AMD, you do the same thing. Your CPI is more, your clock frequency is also more, so your clock cycle time is less. But when you do the multiplication, you get 5 mach per second for AMD and 4 microseconds for Intel. And what it means is that Intel is going to be faster, although it has a lower clock frequency. Right? But you don't really have to do the calculation if you know this equation, because the clock frequency of AMD is 2 times faster than Intel, but also the CPI of Intel is 2.5 times better than the CPI of AMD. So by having this equation, we can see that AMD would have been a slower design, because one of them is 2 times faster, the other one is 2.5 times slower. Any questions? Okay. Now let's talk about some other metrics. One of these metrics is MIPS. So besides the processor MIPS, we also have a metric called MIPS, and this is exactly why they call the processor MIPS too. MIPS is million instructions per second. So MIPS processor is a kind of processor that can execute something around few millions of instructions per second. That's why it's called MIPS. We can also use another metric called MUPS, which is millions of operations per second. It's the same thing, pretty much. And the way we calculate it is very simple. If we have, forget about the million part, we can have IPS, instructions per second, which have the number of instructions divided by execution time. And because we want to add this million to it, we have to divide that by 10 to the 6. If you want to make sense of it, we can have 20 million instructions per second. I'm just reading it in English. Or it can have, 2 million, English is not good, 2 million instructions per second. Or it can have 2 million instructions per second. So I divide this by a million to get MIPS, right? And that's what we're doing here. We have instructions divided by execution time, divided by 10 to the 6, right? Or you can change the execution time to instruction count, multiply by CPI, divided by clock rate. We know these stuff, right? And then we cancel instruction count, clock rate goes up there, and you can get this equation. These conversions I don't really care about because they don't really matter that much. You don't have to memorize this stuff. Even if you know the equations, just play with the equations, right? But the idea here is that we can use MIPS, and the reason we use MIPS, why do we even use MIPS and work with IPS? Because in real world, we don't have 10 instructions. We're talking about millions and millions of instructions, so it just makes it easier for us to talk about it. When we are at a conference, when we have a chip coming out, we don't say 20 trillion instructions per second, just say TOPS, right? So everyone knows that that is the scale that we're talking about. We use MIPS. I introduced TOPS in the next slide too. TOPS is MIPS, the processor. I think it is a pretty old processor. So it was the time that we could execute million instructions per second. Now we are in a point that we can execute trillions of instructions per second. So we have new metrics coming out, right? So, but before getting there, let's talk about energy consumption. So energy consumption is equal to power multiplied by execution time. So power consumption theoretically, if you have a chip, if you have a processor working, and if you measure your power consumption at different points, you keep seeing the same thing. Power consumption doesn't relate to time. Right? This is, you run the code, you get the average power consumption, but if you run it for 50 more seconds, the power consumption is not going to change that much. The energy consumption is what is going to change. So we have energy, which is power, multiplied by execution time. Okay, and then we have metrics like MIPS per milliwatt. This is also another interesting metric that includes everything. So it has execution time because it has million instructions per second, and it also includes some information about the power. So these are more inclusive metrics, and they have, by giving one metric, you give a lot of information to the user, right? So MIPS, we already know that the instruction count divided by execution time divided by 10 to the 6. This is milliwatt, so we multiply it by 10 to the 3 to compensate that for that milli that we have there. And power is energy divided by execution time. So theoretically, for calculating MIPS per milliwatt, you don't need to know the execution time. Right? If you divide these guys, you don't really need that information about the execution time. You can calculate the MIPS per watt without that information. But as I said, these days we're working with processors, especially special purpose processors. For example, one example of that is TPU. Have you guys heard about TPU, a tensor processing unit? A lot of you heard about GPU, graphic processing unit. But TPU is a tensor processing unit, is a kind of processor designed specifically for machine learning workloads. It's designed by Google. You don't expect that because Google is not a chip designer. We have Intel, TSMC, and these companies, AMD, IBM. We know them as chip designer, but Google actually designed this chip. They don't fabricate it, of course, but they design it. And it was proposed, I think, 2016 or 17, if I'm not wrong. So this is designed specifically to do matrix multiplication and vector multiplication, matrix vector multiplication. So the performance of this processor is in range of TOPS, trillions of operations per second. Right? So now if we want to design, for example, in-memory computing architectures, what we do, we compare with TPU. We say, okay, we have designed this in architecture in our lab, and it achieves 4 TOPS per watt, 64 TOPS per watt. You know, these are the numbers that we're getting these days. TPU can achieve something around 2 TOPS per watt right now. And it's, you know, best it can achieve 2 TOPS per watt, 2 trillion operations per second per watt. So it includes a lot of information, as you can see. And the way you can calculate the instruction count, execution time, and power, TOPS is trillion, so you put a 10 to the 12 here to compensate for that. That's another metric. All right, so after knowing these metrics, I want to talk about the second part of this module, which is actually the last part. We have a few more slides, which is about benchmarking. Okay, so now we have the metrics. We now have to compare the processors. We need the workload, right? It's not possible for people to just have their own workload and benchmark their processor. The comparison is not fair. So the idea of benchmarking is coming up with a bunch of workloads that we can run on different types of computer systems and compare them. This process is called benchmarking. Okay? You want to compare two processors, but you want to have specific programs to run on these processes. Benchmarks, if they're good, they have to have a mix of instructions. We can have, for example, arithmetic instructions, graphics, text processing, different applications. That's a good benchmark, right? Because if you have a specific benchmark, and people do it these days too. We also do it in the lab too. For example, we can say we benchmark computer vision tasks. Now, you're not benchmarking the processor, you're benchmarking the processor for specific application. That is what is done in the research level. We do this. We have, for example, edge computing devices, edge AI accelerators, and we benchmark 4 different edge AI accelerators, and that's a benchmarking paper. When we publish the paper, we benchmark it for a specific application. But when you're proposing a processor, a general purpose processor, you have to have a good range of applications. It's not just fair to benchmark that for a specific application. It's a different audience, of course. So I provided this website. You can see that how they benchmark CPU and so on. Idea is very simple. I have a CPU, I run a program, and I measure this and I compare it. Right? It's a very engineering work to do at the CPU level. At the new kind of architecture levels, benchmarking is a very interesting kind of research as well. If you have new designs. Because when you have new designs, people don't know how to benchmark them. So if you publish a paper to talk about this is one way of benchmarking them, you're contributing to the research community and the industry as well. Okay, so SPEC, System Performance Evaluation Corporation, is a very well-known benchmark. A bunch of companies came together, developed benchmarks. We had Intel, AMD, IBM, all these companies, they came together and they wanted to remove the bias. Because if one company designed a workload, they could design it for their own processor. So all these companies came together, designed some benchmarks, and they all agreed to test their computer systems on these benchmarks. This is called SPEC. And you can click on this website. I don't want to go into details of this website, and you can see what it is, see some of the specs, some of the benchmarks that they have. I think I provided a slide that actually shows some of these benchmarks. Yes, for example here. This is some example of an integer benchmark. The program is in C and C++, and the tasks are compression, FPGA placement and routing, chess program, for example, word pressing program, computer visualization. These are different tasks that we run, and these are what they call. We run on these computers, and we see how much power they consume, how long it takes for them to finish the task. We have the same scenario for floating point. So these are 14 of them. They are in Fortran. I'm not sure who is using Fortran now, but C, they have a C code for these tasks too. We have computational fluid dynamics, for example, or neural network image recognition, computational chemistry, image recognition of faces. These are the types of applications that use floating point operations intensively. So they design these programs as a part of the SPEC benchmark, and they run it on these computer systems to measure the power, performance, and so on. So how can we calculate a SPEC ratio? Usually we need to have a reference computer, so they give us information about the reference computer, and we calculate the SPEC ratio based on that reference computer. SPEC ratio is pretty much like performance. It's a relative performance. And this equation that you see here, we're familiar with it because we're familiar with the performance equation. It says SPEC ratio A, execution time on reference computer, divided by execution time on computer A, which is also equal to performance A divided by performance of the reference computer. This is SPEC ratio, right? And you can also use SPEC ratios to, you can ignore this reference computer and directly compare two computer systems by using SPEC ratio A over SPEC ratio B. So this is how it happens, because if you really put this equation here, this execution time of the reference is going to be canceled. So a SPEC ratio A divided by SPEC ratio B is going to be execution time of B divided by execution time of A, which is all equal to performance of A divided by performance of B. So we know this. This is just a term that I want you guys to be familiar with. So if someone says, well, there's a SPEC ratio of A compared to B, what they really mean is, what is the performance of A compared to performance of B? Calculation is exactly the same thing. It's nothing different. Something that is a little bit different is a SPEC score. So SPEC ratio is straightforward to implement. A SPEC score is different. SPEC score is we have computer systems, we have different types of workloads, and we calculate the spec ratio for each of these workloads, and then we get the geometric mean of these spec ratios. So usually when you work with ratios with unitless values, you get the geometric mean, which is you multiply these ratios and get the root n of them if you have n different numbers. This is called geometric mean, and we also calculate mean, but that is usually when you have units, the values that have units, like you want to get the mean of accuracy, for example. So for spec score, we use geometric mean, which is calculating spec ratios, get the root n of them. Okay. It sounds strange, but it's actually pretty straightforward. So you can see it in this example, which is actually the last example in the class. And then we will have some time for Kahoot. So we have two computer systems, A and B, and the reference computer. Okay. So we want to use the reference computer R, which is here, to evaluate two computer systems A and B using the benchmark suite that has 3 workload programs as below: CPU, memory, graphics. So there's one workload designed to test CPU, another one designed to test memory, and another one designed to test graphics in this computer system. These are the numbers that we have. We want to find the spec score, but we want to do it through calculating spec ratios. So if I put this note, instead of express your answer as a ratio of spec scores of system A and B, I'm not looking for you guys calculating the execution time and comparing them. You have to actually calculate the spec ratio. If in the exam I ask for it, I want to see the spec ratio, and then I want to see the geometric mean, right? If it says specifically use a spec score, you have to solve it through a spec ratio. Okay, so if I want to find the spec ratio of A, we said it's going to be spec ratio of A for CPU for this workload is going to be equal to time of the reference computer divided by the time of A, right? So performance of A divided by performance of the reference computer, or execution time of the reference computer divided by execution time of computer A. So if I do this division, 20 divided by 4, this is going to be 5. So spec ratio of A for CPU is 5. Spec ratio of A for memory is going to be 6. 30 divided by 5. The spec ratio of A for graphics is going to be reference divided by A, which is equal to 4. Okay? If we're going to calculate the spec ratios, I'm going to get 5, 6, and 4. Right? So if I want to do the same thing for B, what is the spec ratio here? You tell me. Spec ratio of B for the CPU workload, 4. 20 divided by 5 is 4. For the memory, 5. For the graphics, 3. So we're going to get 4, 5, and 3. Now, we want to calculate the spec score for each of these guys. The spec score of A is 5 divided by 6 divided by 4, and you get the cube root of that, and it gives us 4.92. You obviously need a calculator for that. I can do it. So spec score of B is 4 multiplied by 5 multiplied by 3, and then you get the cube root again. You get 3.9, and if you want to get spec score of A with respect to spec score of B, you divide 4.92 by 30.9, and it's going to be equal to 1.26. And this is your answer. You could have calculated this 1.6 by calculating the execution time as well, but when I specifically say that I want to see spec scores, you have to go through the spec ratio path. All right. Any questions?